Cool, so now we're going to talk about what happens if we connect these capacitors up in series. And it's a little bit more complicated. First of all, we've got to think what actually happens when we start pumping charge onto these things in series. So let's imagine we've got a little power pack, and that's going to pump charge around onto our capacitors, and so we're going to get some pluses here, and those pluses have come from over here. But if we've got a whole lot of negatives over here and some pluses over here, that's going to drive some negatives off these plates, repelled by those, and attract them over to here. And in the same way, we're going to repel some positive charge off that plate. In fact, we say repel positive charge, but in fact what it is just that there's a deficit of electrons. We've lost some electrons from over there. But what's really interesting is that in terms of how much charge has flowed through the power pack, it's only the charge that's moved from the far plate on this capacitor over to the far plate on this capacitor that's actually flowed around the circuit. And so what that means is that the charge on this capacitor is the same as the charge on this capacitor. And that rule applies for capacitors and circuits. The charge on capacitors and circuits is constant. So in fact, Q1 is equal to Q2 is equal to the total charge stored on capacitors in series. We're not adding any more charge as we add more capacitors in series. And so once we have that sorted out, we can now rewrite these equations. We can say that C1 V1 is equal to Q and C2 V2 is equal to Q. And we're trying to work out, we would like to know how much is the total charge that we can store on this combination. So, and so when we look at how that looks, we've got C total is Q total over V total. The Q is going to be the same on all of our capacitors. So Q total is Q1, is Q2. It's the V1 and V2 that add to the V total. But we don't like having an addition on the bottom line of our equation. So we're going to flip the whole thing upside down. We're going to have 1 over C total is equal to V1 plus V2 over Q. And that Q, we know, is the same for the first capacitor and the second capacitor. So we could rewrite that as 1 over C total is V1 over Q1 plus V2 over Q2. And we can notice that V1 over Q1 is the same as 1 over C1. So 1 over C total is 1 over C1 plus 1 over C2. And so that's our equation that we end up with for how to find the total capacitance of capacitors in series. And the consequence of an equation like that is that the total capacitance is always less than the smallest capacitor that's in that combination. And the way we got there is by recognizing that the charge on each capacitor has to be the same, and it has to in fact be equal to the total charge stored, combined with the fact that because they're in series, the voltages add to the total voltage. We put all that together and worked out that our equation for capacitors in series kind of mirrors our equation for resistors in parallel, and vice versa for capacitors in parallel, the equation mirrors our equation that we're familiar with for resistors in series.